Hello and welcome back. So as I mentioned in the previous course, there are many types of diodes, right? And the circuit symbols for the most popular diodes that we use are these one here. Actually, I forgot to include the shiny LED. That's popular too, but the LED in almost all cases is not a critical piece of component in a circuit. Yeah, anyway, the basic and most used diode is the general purpose diode. Then we have the Schottky diode, which is used for high frequency applications. More on that later. And finally we have the Zener diode, which I have to say it's a very fun component to use. A Zener diode is a silicon semiconductor device that permits current to flow in either a forward or reverse direction. That sounds interesting, if you ask me. So let's see what does this Zener has to hide. Now, discussing about the diode circuits, we should look through the graphical representation of the operation of the Zener diode. Normally it is called the voltage current characteristics of a Zener diode. So the Zener diode operates just like a normal diode when in the forward bias mode and has a turn-on voltage of between 0.3 and 0.7 volts. So nothing interesting here. However, when connected in the reverse mode, which is usual in most of its applications, a small leakage current may flow. The Zener diode has a well-defined reverse breakdown voltage at which it starts conducting current and continues operating continuously in the reverse bias mode without getting damaged. So as the reverse voltage increases to the predetermined breakdown voltage, a current starts flowing through the diode, and the current increases to a maximum which is determined by the series resistor, after which it stabilizes and remains constant over a wide range of applied voltage. What is very important for you to understand is that the voltage drop across the diode remains constant over a wide range of voltages, a feature that makes Zener diode suitable for use in voltage regulations. Alright, but what is a voltage regulator? Well, the purpose of a voltage regulator is to keep the voltage in a circuit relatively close to a desired value. So let's say if the breakdown voltage of the Zener is 5 volts, then no matter how much is the source voltage, the voltage drop from this point to this point will be always 5 volts. Of course, the voltage of the power source has to be higher than the breakdown voltage of the Zener, because otherwise there is no point in using the Zener diode. And the Zener diode will be able to basically reduce the power supply voltage to a desired voltage. So I say, let's see a Zener diode in action. So just like how I did in the previous course before doing a simulation, I want to show you something in this datasheet. So a Zener's breakdown voltage can be seen in its datasheet, right? And so for this particular Zener diode, the breakdown voltage, where is it here, is 3.3 to 100. This means that the voltage drop across the diode will always be 3.3 volts, no matter how much is the voltage of the power supply. But if it's higher than 100, then you will damage the poor Zener diode. So how does this voltage regulator circuit work? Well, this resistor here is connected in series with the Zener diode to limit the current flow through the diode. The stabilized output voltage Vout is taken from across the Zener diode, and the Zener diode is connected with its cathode terminal to the positive rail of the DC supply, which means that it is reverse biased and will be operating in its breakdown condition. As you can see, the load is connected in parallel with the Zener diode, so the voltage across the load is always the same as the Zener voltage. You have to know that there is a minimum Zener current for which the stabilization of the voltage is effective, which means that if there's too little current going through the Zener diode, the output voltage might be less than 5.6 volts. So by looking at the datasheet of the Zener diode, you can find a recommended current for which the Zener operates well and also it doesn't heat up. The upper limit of current is of course dependent upon the power rating of the device. So as you can see, the supply voltage must be greater than the breakdown voltage of the Zener diode, and the magic here is that no matter how much is the power supply voltage, the output voltage will always be the breakdown voltage of the Zener diode. One small problem with the Zener diode stabilizer circuits is that the diode can sometimes generate electrical noise on top of the DC supply as it tries to stabilize the voltage. Well, normally this is not a problem for most applications, but the addition of a large value decoupling capacitor across the Zener's output may be required to give additional smoothing. Then, to summarize a little bit, well, a Zener diode is always operated in its reverse bias condition, right? And as such, a simple voltage regulator circuit can be designed using a Zener diode to maintain a constant DC output voltage across the load in spite of variations in the input voltage or changes in the load current. And the stabilized output voltage is always selected to be the same as the breakdown voltage of the diode. So this circuit might be good for some applications, right? But it has a huge drawback. What happens if I change this load to, let's say, 100 ohm? Look what happened. Well, the regulated output voltage is not regulated anymore, and it has dropped from 5.6 volts to just 2.5 volts. How is this possible? Well, as I said, the Zener diode needs a minimum current through it to operate well, and this time the load resistance steals the current from the Zener diode because the current is always following the path of least resistance. So in order to solve this problem, also the other problem with the noise added on the top of the DC voltage is the following circuit. Well, what do we have here? This is the very famous active device called a transistor, which is the core and the heart of digital electronics, and which also has tons of applications in analog circuits. We didn't learn about this component yet, I know, so when we learn about it, you can come back and check this circuit out. So the load here is again 10 kilo, but this time when I reduce its value to 100, the voltage doesn't drop at all. I just remembered that this circuit has another huge disadvantage, and that is this resistor here, which is used to limit the current for the Zener diode, is not only limiting the current for the Zener diode, it also limits the current for the whole circuit. So the maximum current that can flow to the load is basically 15 volts divided by 500, and from this some goes to the Zener, some to the load, right? If you design this resistor too small, the current through the Zener will be too high and you will damage the Zener diode. On the other hand, if this value is too high, the current that goes to the load will be small. So as you see, it's all about a compromise. So this circuit solves all the problems. The resistor value, as you can see, can be much higher, so it reduces the power dissipation of the Zener, also allowing a higher output current.